Hi, this is part 4 of my series on linear viscoelasticity. Today I'm going to focus on something that I call a Prony Series spectrum. And this may sound like a really weird and mathematical subject, but I can assure you this is actually very useful and it will help you a lot in your linear viscoelastic material model. So please make sure you listen in on this one because this is a really interesting topic that a lot of people don't know about. So let me get started by just introducing again the concept of a Prony series. This is what your finite element program will ask for. In Abacus, you specify these G parameters in this way. So GR is the normalized relaxation modulus. How much the stress is decaying as a function of time in the stress relaxation experiment. And it's an exponential form that's typically represented in this way. In answers, you'll see that the equation is similar, but not exactly written the same way. And this is typical. Finite element programs kind of write these equations slightly different between them. So pay attention to that. But what's interesting is to kind of understand what this is all about. So if we plot an experimental stress relaxation response like this, and then we fit this Prony series to it, we can look at it down here. Well, at the graph, it's very little relaxation at short time, and very little relaxation at long times. And it's in the middle of this graph that all the change happens. So we can see that here at really short tau I values, the GI value is very small. So this is exactly what we see in the graph. Then around 1 second here in time, we see a very large drop in the stress, and that's why the GI values are very large. So this is typically what one sees experimentally for a Prony series. The problem here is that we need to find all of these numbers. So like there's a lot of numbers here, and the numbers are not independent of each other. The time values are sort of distributed over some time period of interest, but the GI values are not independent. The next value in this series tend to be between the previous and the next, and it's kind of a smooth function. There must be a better way to do this than to have to specify each of these values individually. And that's the whole concept of a Prony series spectrum. We can do it once for all, and that makes it much easier to work with these Prony series. So here's how it works. So if you plot this data here, so this is the tau on the x-axis I'm going to plot, and then GI, the relaxation value, on the y-axis. Typically, you will see experimentally something like this. There is at really short times, there is not much relaxation occurring. Really long, it's not. And then most of it happens in the middle. So the spectrum curve looks like this. So if we can come up with a mathematical equation that tells us how this shape occurs, we don't need to specify all of these numbers. We just need to specify the parameters of this equation. So in real life, this would be something like this. Here's the spectrum function that represents how the relaxation occurs at different times. We need to discretize this, though, because that's what Abacus Answers and LS-DYNA, all of these finite element codes do. You have to discretize it into discrete time points, and you need to tell the software what are the G values at those points. But we can discretize it based on this mathematical equation that I haven't shown you yet. But if we have 7 points here, there will be 1 per decade, and they will be sort of like this. If we pick 10 points, they will be distributed sort of like this. We'll see that you want to make sure you have enough points, right? Because this one happened to have one in the peak, that's one or two here. The shapes are similar, but you need to make sure you have enough of these points, and each point would be a Prony series term. The other thing to keep in mind when you discretize the curve like this is that one value of high importance is the sum of all the GI values, because that's how much the stress will eventually decay if you wait long enough time. So it's not only the individual values, but also the sum of the values is super important. So I often like to specify what this max value should be in addition to the individual relative contributions of this curve here. So let's talk about how you would do this in practice. Answers, Abacus, etc. don't really allow you to specify the spectrum. But in MCalibration, the software we have developed here at Polymer FM, you can, and this is really nice. We use the following function for the relaxation spectrum here. It's an exponential function of this form. T is the time on the x-axis. Tm is the mean value. That's where the peak occurs. And Ts is the standard deviation. Basically, how wide is the spectrum function here. And then we have a shape parameter b to sort of tweak the shape a little bit if you need to. So that's the mathematical equation. We then discretize it by specifying how many points are there in our target Prony series. And that's it. Much easier to deal with because we have a small number of parameters and not this huge number of Prony parameters that we need to specify. So let's take a look how this works in practice. So I just open a window of MCalibration here. And in this case, I have just a single data set here. It's a stress relaxation experiment where I loaded it up and held it for a while, about 1,000 seconds in this case. And then I specified an ANSYS linear elastic Prony series with one Prony series parameter. And here it is. So it's a Young's modulus of 10. It should relax 90% in about 1 second. And that's what we see here. If I click around once, this is the response that we get. And it's nothing particularly exciting about it. A single Prony series terms will do this, as this is the significant result that doesn't usually match the data, because you can't specify the whole response at longer times. So experimentally, it doesn't always happen this quick. You need to have a different shape to this curve. And that's why people come up with the Prony series to superimpose a number of these exponential curves. Now, with a spectrum, things get much easier. So let me open a window of MCalibration with a spectrum. So here is a spectrum curve. So this is Abacus linear elastic Prony Spectrum. And you specify spectrum in the definition in here. And then we have the same parameters as before. If I make the mean value of the spectrum 1, which is what we had in the one Prony series example, if I make the standard deviation very small, perhaps this, and we run this one, we'll see that we get a response here that has now 20 Prony series terms in it. We discretize it into 20 terms. But the standard deviation is so small, so we basically will get the same result as we get with a single Prony series terms. They are very close together. But if we change the standard deviation of this, we say we make it 20 here, then we see we get a much more broad spectrum response. And this is now very easy to use. You can calibrate this to experimental data, whatever data that is. Could be DMA data, it could be frequency data, it could be stress relaxation data, creep data, strain rate data, whatever data you have, you can calibrate the spectrum representation much quicker, much easier. And this can also be calibrated with the time temperature superposition idea. So this idea with the spectrum is very powerful, because that's how really materials behave. So to summarize, using a Prony series for linear viscoelasticity is pretty inconvenient, because you can have as many as 20 or even more Prony series terms, and they are usually following a very specific mathematical shape. So instead of doing that, using a spectrum where you specify the shape of the spectrum using a small number of parameters is usually far better. And I would encourage you to try this out in the latest version of MCalibration. This, I think, will help you tremendously when it comes to actually using linear viscoelasticity in your finite element simulations. If you have any questions, you can ask them below.